Okay, in this video here, what we're going to look at is the new um, practical exercise that a few of us did in the vineyard at Growling Frog. And in this exercise, we are designing a irrigation system, a drip irrigation system for that vineyard. This irrigation system involves a main line which runs up the eastern flank of the vineyard with stemming from a pump which is on the dam at the base of the vineyard. Then we run sublines into the vineyard at 3 locations along the main line, dividing the block into 3, and then we run laterals from these sublines, which will actually have the drippers on, which will provide the irrigation to the vines. I'm going to use the word vines, but this exercise is valid for any dripper system in any type of crop. So it's universally applicable because it's all just about moving water or liquids around. The number of questions we had on the day was about, oh, can't we use calculators, irrigation calculators? Well, this is actually the maths behind some of the irrigation calculators, and not all those calculators are correct. A lot of them are designed, they're on websites for companies that sell things like irrigation piping and tubing and drippers. So they're designed to encourage you to use their equipment rather than find the most optimized solution for your irrigation requirements. Why are we dividing this cropping system, this vineyard, into 3? It's because ideally our drip lines, our laterals, will not be greater than 60 metres. When they're longer than 60 metres, it's hard to keep regular pressure all the way along the lateral, and can also mean that the dynamic head becomes too great and the pressure required to push the water at the adequate pressure along that lateral can be too great for the lateral equipment making up that lateral itself. So for example, it might blow a dripper out of the actual lateral line. I'm going to go through this spreadsheet, which is the centerpiece. The actual aerial image of the vineyard or cropping system is found in the notes for this exercise. But really, the numbers you put in, I mean, you can do it for any system you want. You can do it for your own farm or a glasshouse environment. Just make sure it has a main line, a subline, and laterals. In this case, the laterals are going to be running from uphill and go down slope. We had a couple of questions about, can you just run laterals both sides of the subline and have that in the middle? And that will work, certainly. Using gravity for this one will sort of be a little bit easier for the exercise, and also pretty easy to clear the lines as well, flush the lines when you're just running off gravity as well, so you can empty the system pretty easily. So the exercise that we did on the field day required measuring the vertical distance between the dam at the base of the vineyard and the top of the vineyard. That's because we need to know the static head. So when we're working out the total head, in this exercise we need to find out what the total head of this system is, so the total pressure that a pump would need to overcome. The components of total head we know is dynamic head and static head. Static head is purely the effort that the pump needs to go to overcome gravity, and that's to do with the meters above, or I suppose the meters of potential energy that we need to provide to the water to move it. And so in this system here, even though we have laterals of different elevations above the pump, now the pump itself has to overcome the overall static head of the system, which is the highest point. So the static head will just be the maximum vertical distance that the water has to move. In this case, we calculated it using a clinometry. I don't even know if that's a word, but we used a clinometer to calculate the vertical rise from where the pump would be to the top of the irrigation system. We had some varying answers, but let's say it was 20 meters. So I'm going to put that static head in here. Actually, I'm just going to type that into this spreadsheet. It's the first time I've used this spreadsheet that I designed myself, so I'm still adding a little bit to it, and you feel free to optimize it however you like. So let's say the static head is 10 meters in this system, and that is what we calculated, and that's the vertical distance between the dam at the bottom, the pump, sorry, and the top of the irrigation system. It probably seems a little bit low. Let's put that at 15 meters, and then I'll do a total head here. My internet will work. Actually, for interest's sake, I'm recording this in Krakow in Poland. It's a very nice city, beautiful old city. If anyone's been to Krakow, send me an email. I'd love to hear about your experience and any good places for lunch. Let's get an insert, make a little bit of room here. So this spreadsheet's a classic Alistair Reid spreadsheet where I really tease out every calculation, and I have full visibility of every number that goes into every formula, and that's really important. I talked about it on the field day because it allows us to find errors quite simply where there's a ridiculous number. So we'll go through it, and then we're going to take it all the way. This is actually beyond what the exercise asks you for, but I think it's quite interesting. We're going to go and actually no, it's actually using the exercise, isn't it? We're going to we're going to go a little bit beyond what's in the exercise. So we're going to calculate the evapotranspiration. So that's the evaporation and transpiration that occurs in the months from November to April in this case. So we've gone 6 months. So that's water that's lost directly from evaporation from the soil and through the plant through transpiration. So from the soil into the plant and out the stomata back into the atmosphere. That's what we call evapotranspiration. Evapotranspiration is provided to us by the Bureau of Meteorology. And what it is I think, from memory, it's the amount of evapotranspiration on a given day from a metre squared patch of a particular pasture of known height. So if you had a metre squared of this crop, this pasture, how much water would actually be lost from the soil through evaporation and transpiration? So it shows how much soil water is being lost, not including that which might be draining down deeper into the profile away from the roots. So obviously using evapotranspiration related to pasture doesn't necessarily apply to, say, something like a grapevine, or I discussed maybe using a cabbage if you're more of an agricultural, you're not interested in grapevines. So what we use is things called crop factors, and what that does is adjust this universal evapotranspiration figure into one more applicable to our crop of interest. And they're published by the FAO, and you can do your own, and if you go into the academic journals for your particular agricultural field, you'll find some crop factors which have been designed for particular environments and different clones or subspecies or varieties. Right, so let's go through the system, and wherever there's yellow, I'm pretty sure, hopefully if I've done it right, is where we need to add some numbers. So first of all, it says emitter spacing. So how far apart are the drippers on the drip line? In this case, we're doing one dripper per vine, and I think from memory, in this case, each vine was about 1.5 meters apart. So I'll put 1.5 there. But you might be doing double that, so it might be 75 centimeters apart, or it might be even more than that if it's in a glasshouse environment. It might be 10 centimeters, so you'd have a dripper every 10 centimeters along lateral. Generally, you don't want, I think it's more than 120 drippers on a lateral, so if you did have a 60 meter, so your maximum length for the lateral, you wouldn't have them more than every 0.5 meter along that lateral. However, if your lateral's shorter, then you can put a heap more on there. So let's say if you had a 10 meter lateral, you could have one every 10 centimeters. No, 12 meter one, you'd have 120. So the number of laterals, so this one is asking, this spreadsheet is for calculations of pressure requirements of each lateral, Although we're going to put in the total number of laterals in this particular system, so we can do some calculations down the track here. So the total number of laterals is the number of sublines multiplied by the number of laterals per subline. So we could actually put that in so we further optimize this spreadsheet. Let's do that. I might actually break this video into two. Might be number of sublines might be a bit too big. Number of sublines, the units are just a number, so we've got 3 of them, and then laterals per subline, the number. We've got 15. There's 15 rows, so we've got 1 lateral per row at each subline. So number of laterals equals that times that. Remember, if we keep any, we try to avoid having any calculations done by anything other than Microsoft Excel. Get Excel to do all the calculations, because that means you can use the spreadsheet for modeling. Row spacings, that's the distance between rows. We actually need that for some calculations down the track, I think. So row spacing is 2.4 meters. Yeah, that's right. Emitter flow liters per hour. I've gone 2. So it's normally between 2 and 20. Between 2 and 3 is pretty normal, so let's get 3. Actually, we'll start with 2, and we'll have a look how it changes things. So each dripper is doing that much per minute. That's liters per minute. The diameter of the clear pipe not obstructed by the emitter. So in some dripper systems, you actually plug the dripper in to the hose, and then the barb actually sticks into the hose and actually effectively narrows the diameter of the pipe at that particular location, which increases the turbulence. So we need to factor that into our calculations down the track. So we need to tell this spreadsheet how much diameter of clear pipe is there above the emitter. In this case, these emitters are flush against the pipe, so there's no barb in there, so I've just made it the same as the diameter of the pipe itself. So the diameter of the pipe itself is there should be a 0 there, I think. Oh yeah. I'm just gonna have to change this spreadsheet while I think of it. Okay. And then you can use this version of the spreadsheet. So C26. That one there. I'm going to change C26 to this cell here. It's actually an incorrect component of this spreadsheet. And I'm going to this one here is now equals the diameter of the pipe minus the length of the dripper barb. So in this case, we don't have a dripper barb, so it's 0.0127 minus 0. Okay, so let's go back up there. Mainline length. So our mainline goes up the whole way up the side of the vineyard. So let's say it's 160 meters. Now we're doing a calculation for one lateral, only one of the laterals. So what we need to know is how much of that main line is contributed by each lateral. So it's just the main line length divided by the number of laterals. And that's all done for us. Sub-main length. Sub-main length is the number of laterals times the row length. So we could probably just do that ourselves because it's multiplied by the number of submains. So let's go laterals per subline is 15 multiplied by the number of sublines is 3 by the row spacing is 2.4. That'll actually give us the total length of subline. So it's 108 meters. So actually that will calculate ourselves. So again, what's the contribution of this lateral to total submain? 2.4 meters per subline. Should be subline. Some people call them submains. So Actually, based on the emitter flow, we can actually calculate what that is in effective rainfall. So effectively, we're applying 1 mil of rain per hour. Total emitter number is the number of laterals multiplied by no, this is the number of emitters per lateral, isn't it? In our case, each lateral is going to be about 60 meters long with 60 vines. So I've just put 60 in there. That might change though, depending on your system. So that's the number of drippers on each lateral. So I've put there's 60 drippers on the lateral. Okay, so based on our desired emitter flow, and we can change that emitter flow by increasing pressure in the system or getting different dripper types. These are the flow rates. We need flow rate in cubic meters per second for some of the formula. So I've got all those calculated. So you have a quick look at those, and if any of them there looks silly, then we can see that there will be an error. Here we can type in the pipe diameter in inches because it's often quoted in inches. So I put it as ½ inch, and which gives us the diameter in meters. If it's quoted in meters, you just need to hard enter it into there. Average length of the dripper is 0 because there's no dripper barb. And it's got cross-sectional area of the hose already calculated. This is just like in the pump one. Then we turn it into velocity. Velocity is distance over time, whereas flow rate is volume over time. So we move it to distance over time. And then we need to know the viscosity of the water, because that actually changes the turbulence within the pipe as the water moves, which changes the dynamic head. So we actually need to put in the universal viscosity of water, the kinematic viscosity of water, which is 1.0034. Now I did that from memory, and that might actually be wrong, so feel free to double check that. So all liquids have different viscosity, and also it changes with temperature. This one here is at 20 degrees. I should indicate that somewhere. Maybe I'll put that here. 20 C. Horizontal footprint of the emitter. So this is actually this is a number that you've sort of got to either find out or come up with yourself. This is the length of the pipe, which is influenced by the emitter. So how much does it make the water turbulent around the emitter due to the emitter being there? I've put it there as 5 centimeters. It doesn't make a huge contribution to the final dynamic head, so you can actually change that. I think if we just did that as 1 centimeter, won't change it too much. Yeah, it doesn't change it much at all. So loss due to one emitter, this is in meters of head, so this is the amount of pressure we lose for each emitter. So 0.0078 meters, so not a lot per emitter. Hose length is 60 meters, so that's our lateral. Actually need to change that a little bit. That's actually the lateral length. That should be the lateral length plus the subline contribution plus the mainline contribution. So let's change that. Equals subline contribution plus mainline contribution plus the length of the lateral. I suppose we can just do it as the emitter number multiplied by the emitter spacing. It occurs to me that I've got the wrong emitter number there. It should be 40 if they're every 1.5 meters along the lateral, and the lateral is 60 meters long. So the effective hose length, so it's the amount of length of hose that the water has to pass through to get through all these drippers, is 65.95 meters. Let's get rid of some pesky decimal places. Okay, so friction loss So within all this system, we're losing 0.00544 meters of head pressure per meter of hose. So head loss in the lateral due to the pipe itself is 0.3585. Head loss due to all the emitters is 0.1556. So the dynamic head within these laterals is 0.5141. So the lateral itself and the subline to get it there is adding about half a meter of pressure. So not a huge amount, but what if we did it, so this is per lateral. What about we did it for the total system? So I put the static head here as 15 meters. Yeah, that's right. That's per lateral. What if we want the total head for the entire system? In meters. So it's going to be the same static head, isn't it? Because it's still having to lift at 15 meters. But this time it's the dynamic head times the number of laterals, because that's per lateral. 45. So we can see here that actually the dynamic head is contributing to more pressure requirements in this system than the static head itself. So the vertical rise contribution is less than half that of the total of the dynamic head. So the dynamic head, calculating the dynamic head here is really important. So the overall head in the system is 38.14 meters as we calculated. So we need a pump that would deliver 38.14 meters of pressure. And then we'd need a flow rate of, so each lateral requires that much per hour. So we can multiply our number of laterals by that. So 3,600 litres per hour. So that's not a huge volume to deliver in the thought. So total head of the system 38.14. That's cool. All right, so let's. I'm gonna finish this video now. I'm just gonna save that so I can post it back up, and then I'll do the second video, which will be on the evapotranspiration.